Obviously we only have like 13 minutes left. I get that. But it'll be nice for us to start the idea of electron transfer theory so that on Tuesday we can just kind of hit the ground running and we can start doing things with half reactions. Now, you don't know what a half reaction is, and that's totally fine. But we will start talking about half reactions right away. So because redox reactions always involve a transfer of electrons from one thing to another, do you agree that whenever something loses electrons, something else must be gaining those electrons? Do you agree?
Yes.
And the total number of electrons lost must equal the total number of electrons gained. That's where the lowest common multiple comes in. Do you agree with that?
Yes.
Okay. So as long as we understand that principle, that's the basic idea behind electron transfer theory. Electrons are being transferred from one thing to another. If this thing gains 3 electrons, this thing has to lose 3 electrons. It's fairly straightforward. What we're going to do is we're going to represent reactions by using half reactions. So what I want you to think about in this reaction is, what is the oxidation state of zinc here? It's 0, right? What is the oxidation state of the hydrogen in hydrogen chloride? +1, which means the chloride is -1. What's the oxidation state of zinc in zinc chloride? +2, and chlorine -1, and then hydrogen gas 0. Good. So what we're going to do is let's try and identify, well, what thing in here isn't changing? Is there anything that's not changing in here? Yeah, the chloride is not changing. Do you see how it's partnered up with the hydrogen and then it gets partnered up with the zinc, but really it's not doing anything? What do we call something that doesn't do anything?
A bystander.
A spectator, not a bystander. Did you say a helpful witness?
An eligible witness.
Oh. Okay, so let's try and group these things together. What does the zinc start out as? Zinc metal, zinc atoms, and what is it turning into? Zinc 2+ ions, right? So let's write that out. Zinc metal turns into zinc 2+ ions. Does this chemical reaction make sense to you? No, it shouldn't. The way it's written right now, there's one glaring problem with it. Matthew, what was that? What's the problem?
You should throw in some electrons.
I don't know if you heard what he said, but he put his hand up because he wanted to answer the question, and then Jordy said, we're just going to toss in some electrons. And then Matthew awkwardly looked at Jordy and said, we're just going to throw in some electrons. Where are you going to throw in some electrons, Matthew? Matt, where are you going to throw electrons in?
Probably on the side of the 2+.
Why?
Because you want to balance it.
Because you want to balance the charge. So how many electrons should we put there?
I'd probably throw in 2.
Yeah, let's throw in 2. Good job. So 2 electrons. This is what we call a half reaction. Can you understand how this is showing us half of the story of this reaction? So this is what we call a half reaction. Now let's try, okay, what's hydrogen starting out as? A hydrogen plus. Really, that's what it's starting out as. And what is it turning into? Hydrogen gas atoms, right? So, but we have to keep the formula the same, H2 gas. So let's balance this. There's a couple glaring problems with this. There's not one problem, there's 2 problems. Joe, what's one of the problems?
Mass.
The conservation of mass is not being followed right now. Correct. So if I have 2 hydrogens, what do I need on the other side? 2 hydrogens. Now that we've followed the law of conservation of mass, go ahead. Now we have to follow the law of conservation of charge. So where are we going to put electrons? On the left-hand side. Do you agree that if something is losing electrons, something else has to be gaining electrons? Which one is losing and which one is gaining here? Is the zinc gaining or losing electrons?
Losing.
The zinc is not combining with electrons, right? It's not being added to electrons. It's turning into something, and it's releasing electrons. So this right here indicates that we are losing electrons. Max.
Wouldn't it still kind of make sense if you put the electrons on the other side? Because then it'd be like 2 hydrogen ions, like R, hydrogen plus the missing 2 electrons.
No, because what you're saying by putting these electrons over here is that we're saying that 2 hydrogen ions turn into a hydrogen molecule with 2 atoms, and it also releases to the environment 2 electrons. But that doesn't make sense. Do these hydrogen ions have any electrons to give away? They don't. These are 2 protons, right? Hydrogen ions are protons. 2 protons don't have electrons to give away. So this is the way you need to think about these half reactions, is that if I combine 2 electrons with 2 hydrogen ions, I can make 2 hydrogen atoms. Is that okay? Yeah. So if I see electrons in the product side, that means we're releasing electrons, we're losing electrons. If I see electrons in the reactant side, that means we must be gaining electrons, or this is reduction. So hopefully we're okay with that. What's being oxidized in here? The zinc. The zinc is being oxidized, and what's being reduced? The hydrogen ions specifically. The hydrogen ions are being reduced. Okay. A half reaction is a balanced chemical equation that represents either the loss or gain of electrons. Perfect. Every redox reaction can be written as 2 separate half reactions. One is a redox half reaction, and one is an oxidation half reaction. In the previous example, identify which half is oxidation, which half is reduction, blah, 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 blah. Let's do another one.
Can we just go back for like 2 seconds?
Okay, let's go back for 2 seconds.
We have the aqueous and then it turns into gas. Did we just talk about that or?
Yeah, this
Yeah.
goes from aqueous to gas.
Yes, that's it.
But that's because when I place a solid chunk of zinc into any strong acid,
Yeah?
you will start to produce bubbles of hydrogen gas.
Okay.
The acid reacts with the solid piece of metal, and we see bubbles, and the bubbles that are forming is the hydrogen gas.
Alright.
What is hydrogen's state of matter at room temperature, Sanjana? What is its state of matter? What is the
gas.
Yeah, it's a gas. So anytime we make hydrogen atoms, hydrogen, not the ions, but anytime we make hydrogen atoms, at room temperature, it will be a gas.
Okay.
Okay, so these half reactions can be written always. We can just take a reaction and split it up into 2 half reactions. So all you have to do is look at one thing and see what does it turn into. Look at another thing, what does it turn into, and that's your 2 half reactions. You have a table of half reactions can be found in the data booklet. It's on the page before your acid table, so this is on page 7. I would like you to look at page 7 on the data booklet.
That scared me.
Please don't get lost in how much information is being given on this table. Would you agree there's a lot going on in this table.
Well,
What do we have? On the left-hand side, kind of the whole left-hand 2/3, we have half reactions. And they're all written, every single one of them is written as a reduction half reaction. Every single one of these is written as a reduction half reaction. Can you provide for me an explanation as to why they're always written as a half reaction, or as a reduction half reaction? Sophia? Yeah, every single one of these is gaining electrons, and we just want to write them all as reduction half reactions because that just standardizes it. We just get used to all of them being written as reduction half reactions. Now over on the side, we've got voltages that are applied to them. I need you to know that we're not going to be dealing with these in chapter 13, but we will deal with them in chapter 14. So after we have our chapter exam in like a couple weeks here, I don't know, I can't remember when we're going to do it. After we have our chapter exam, then we'll start dealing with these voltages. But right now, all I need you to understand is every single one of these are written as a half reaction. There's really complicated ones, and then there's really, really easy ones. Like, let's go all the way down to the bottom. This very bottom half reaction, does it make sense that lithium, when it gains an electron, turns into lithium metal?
yes.
Yeah, no problem. But then there's really complicated half reactions, like sulfate plus water combines with 2 electrons to give you sulfite and 2 hydroxides. What all of these have in common is that they all follow the law of conservation of mass, and they all follow the law of conservation of charge. So it's important to keep that in the back of our minds as we talk about this. What I want you to do, the reactions are shown as reduction half reactions, but they can be reversed. We're going to talk about one thing here. Just calm down. It'll be okay. Silver ions turning into silver atoms. Where do you see silver anywhere on that sheet? Ag. So where do you see Ag anywhere on this sheet? Ag2S. So that's silver sulfide, right?
Yeah.
Is there silver ions somewhere? Right here. Silver ions reacting with an electron to turn into silver atoms, right? So we could write that down. Silver ions reacting with an electron. Where do you see copper atoms turning into copper 2 ions?
Right, kind of below it.
It's right kind of below it, right? But is it written this exact same way?
No.
We have to reverse this reaction. We have to start with copper metal, and it has to produce 2 electrons and a copper 2 ion. Thank you, Shohei. We'll finish this obviously on Tuesday. That assignment's due on Tuesday. If you finished it already, hand it in. If you didn't finish it, get it done, please. Have a good weekend. Have a good Thanksgiving.
We all go for Halloween.
Oh, I guess